Hello, my name is Andrew Kucher, and today I am going to be solving problem 6.19 from Fundamentals of Heat and Mass Transfer. Uh, though you can see the problem in front of you, I'm just going to read it off so we're all on the same page. To a good approximation, the dynamic viscosity mu, thermal conductivity K, and the specific heat Cp are independent of pressure. In what manner do the kinematic viscosity V and the thermal diffusivity alpha vary with the pressure for an incompressible liquid and an ideal gas? That's part A. Determine alpha of air at 250 K for pressures of 1, 5, and 10 atmospheres. Part 2, B. And for part C, assuming a transition Reynolds number of 5 times 10 to the 5, determine the distance from the leading edge of a flat plate at which transition will occur for air at the same conditions as part B, with a U infinity of 2 meters per second. So my solution for this is right here. So obviously start off with the givens, the Reynolds number, the atmosphere is the pressure given, and the uh, in velocity at infinity. And also just some assumptions. Steady state for this is a pretty solid one. Constant property is also very solid. They give us the ideal gas. And the Reynolds number is equal to 5 times 10 to the 5, specifically for the case of a plate. And just saving myself some time, I put the properties of air at 350 K right here. So you can see the viscosity, conductivity, CP, and density rho. Now for the solution, part A, I think this one is the hardest because it's a lot more open-ended than some of the others, and it also is used in the others. Specifically, what this is asking for us is to show the how whether or not an ideal gas or incompressible liquid are dependent on pressure for diffusivity and kinematic viscosity. So as you can see here, I kind of have the two columns. So I show the ideal gas equations and the incompressible liquid equations. Uh, so for ideal gas law, pressure equals density times RT, and obviously solve that for pressure. Uh, excuse me, for density, and for the kinematic viscosity, that is mu over rho. So for ideal gas, you plug in rho, so you get mu times RT over pressure. So the kinematic viscosity is proportional to 1 over pressure, or P to the negative 1. For alpha diffusivity, the equation is conductivity over uh, density times Cp, or C. And plugging in the density of an ideal gas, you get diffusivity equals K times RT over pressure times C, or Cp, which is the same case as kinematic viscosity. It is directly proportional to 1 over pressure, or P to the negative 1. However, for an incompressible liquid, the density is constant. It does not change. It's incompressible. You can't really change the density at all. So the kinematic viscosity and diffusivity are not impacted at all by pressure, because the pressure for an incompressible liquid, literally from the name, you can't compress it any further. So as much as you increase the pressure, you cannot change the volume of the space. So it's completely divorced of any pressure effects. Now, for part B, they asked for values of diffusivity for air at the 3 atmospheric pressures. So at 1 atmosphere, um, again, the equation from above, you use the variables and properties given above for the air at 350 K at 1 atmosphere. And these are the values you get, which I got 29.9 times 10 to the negative 6 for diffusivity, And just to double check the units, I also put in the units for each of the individual components and verified that they do end up resulting in the proper units, which is meters squared per second. Now, where it gets interesting is for the higher atmospheric pressures, you don't need to recalculate or refine the atmospheric conditions because using the properties determined above where it's proportional to pressure, all you got to do is divide the calculated pressure for one atmosphere by 5 to get the diffusivity at a higher atmospheric value, which in this case is 5.98 times 10 to the negative 6. And oh, I made a typo there. I was supposed to write 10 for 10 atmospheres instead of 5. My apologies. The value is still correct though. 2.99 times 10 to the negative 6 meters per second. I just made an error in my write-up. And same thing for the distance, xc, where transition occurs. The equation is xc times u infinity over kinematic viscosity v equals 5 times 10 to the 5. Obviously solve that for xc, you end up with 5 times xc equals 5 times 10 to the 5 times kinematic viscosity divided by essentially 2. But you need kinematic viscosity in order to get that, so you do the exact same thing we did above. So kinematic viscosity, as the equation is listed here, is mu over rho. So mu from these tables up here are 208.2 times 10 to the negative 7 Newton seconds per meter squared. So you divide that by the density of air at this pressure, which is 0.995, and you get a kinematic viscosity at 1 atmosphere of 20.92 times 10 to the negative 6 meters squared per second. Doing the same thing as we did for diffusivity, divide by 5, you get 4.18 times 10 to the negative 6, and divide by 10, well, obviously that should be 2.09 times 10 to the negative 6. And plugging into the equation above, you get, for the distances involved at 1 atmosphere, you get about 5 meters. At 5 atmospheres, you get 1 meter, and at 10 atmosphere, you get approximately half a meter for the transition region. All right. I'll just leave these up for a hot second to let anybody who wants to view it. And yeah, overall, a pretty quick question, but again, the part A might be a little bit hard to wrap your head around simply because it's more open-ended. You're not exactly doing plug and play with the equations per se, but overall, still a simple question. So thank you for joining me. Have a nice day.